These are the notes for day 11. We will spend 2 days on optimization, and this is obviously the first day. The first day examples are just 2 of them, but they take a little while. So question 1 says 2 points on this curve have opposite x values, x and negative x. Find the points making the slope of the line joining them the greatest. So here's a curve. I just picked a point anywhere and called it x. And then if I go to the opposite location, negative x, take the 2 values on the curve, connect them, and I want to find where that slope could be a maximum. So the function I'm looking for is slope, which we know is change in y over change in x. I take my 2 y values, x cubed, 1 plus x to the 4th, minus same thing but with x replaced with negative x here and there. And now I do a bunch of divided by the change in x, which is x minus a negative x. Do a little bit of simplifying, we wind up with this fraction, multiply top and bottom by 1 over 2x, and you wind up with this. This is the function for slope. Optimization means that you want to set up a function and then find a minimum or a maximum for that function. So if this is the slope function, I'm going to change it into a product because I like the product rule better than the quotient rule. And to find the max or min of any function, we need to take the first derivative. So pause the video here, find the first derivative, try and find the critical values, and then decide whether or not you're going to find the max or min using the first derivative test or the second derivative test. So hopefully you did the product rule correctly and got something that looks like this. Again, in order to find roots or critical numbers, we need to factor out the smallest exponent. So 1 plus x to the 4th with a negative 2 is smallest, and 2x is also smallest, so I'm going to factor out both of those. I also decided to factor out a negative so that my first term would become positive, and I get this quantity times that quantity, which is written like this. So critical numbers are 0 because of the negative 2x, plus or minus 1 because of that quantity in the numerator, and then the denominator is always positive and has no real roots, so there are 3 critical numbers that we need to test. Okay, taking the second derivative of that would be a bit of a mess, so I think I'm going to opt for the first derivative test. So take the critical numbers, put them on a number line, test values on either side of those critical numbers, and decide where your function is increasing and decreasing. Pause the video and do those steps, and the answer will be here in a second. So supporting work for the first derivative test, critical numbers are negative 1, 0, and 1. Values that I'm testing, negative 2, negative 1/2, 1/2, and 2. Plugging them into the first derivative function right here, all we really care about is whether the first derivative is positive or negative. So as I plug negative 2 into 1, 2, 3 locations, all I care about is the sign. And if you look at the denominator, that's always positive. So for each of my test values, I can immediately make the denominator positive. When I plug in a negative 2, this is positive, and this is also positive, so I get positive for those 2 factors. Overall, the first derivative is positive, which means the slope function is increasing. Repeating that process when I plug in numbers, double checking all my work because it's easy to make a silly mistake. It doesn't always do this, but it turns out this function goes from increasing to decreasing to increasing to decreasing based on positive, negative first derivatives. So now to answer the question, find the points making the slope of the line joining them the greatest. Use this information to answer the question. Again, pause the video, write down your answer, and I'll reveal the answer in a second. So by the first derivative test, we have maximums at negative 1 and positive 1 because the function is changing from increasing to decreasing in those locations, which makes sense because if x is 1 or if x is negative 1, I'm going to get these 2 values here. The minimum is that x equals 0, but we weren't asked for that. So when I take plus or minus 1 and plug it into the function, we wind up with 1/2. And at this point here, I need to go back and answer the question. Did they ask for the max min or did they ask for a point? And they said find the point. So the correct answer is plus or minus 1 and 1/2. At those points, the value of this function is the value of the slope between those 2 points is a maximum. So that's the first example. So the biggest challenge with optimization problems isn't so much the calculus, it's setting up the situations because for the most part you're just given words and you need to convert that into math somehow. So I've color-coded the steps for this problem. A north-south highway intersects an east-west highway at a point P. So I have axes drawn in gray and there's a point P where they intersect. An automobile crosses P at 10 a.m. traveling east at a constant speed of 20 miles per hour. So at P, traveling east, at a constant speed of 20 miles per hour, I have an arrow here. This is my first automobile, okay? The rate of change in the x direction is positive 20. That's used quite often in problems like this, but for this problem, we don't really need this. But it's a good thing to keep in mind. If a car travels at constant speed of 20 miles per hour, dx dt is plus 20, okay? What I do need is a distance. So if I take rate times time and say 20 times t, that's the distance that that first car is traveling. Same instant, another automobile is 2 miles north of P. So I put a dot at 2 directly north of P, and it says traveling south at 50 miles per hour. So this distance here is 50t. The distance that I need, though, I don't know yet, so I'm going to have to figure that out in a minute. But start at 2, travel south, 50 times t, rate times time is the distance. Find the time at which they are closest to each other and approximate the minimum distance between the automobiles. So as the second car travels south and as the first car travels east, there's a distance between them, so I drew that line there. In order to find that distance, we're going to use Pythagorean theorem. I know this distance. I get this one by saying, well, the whole thing is 2, and it's traveled 50 times t, so the red highlighted distance is 2 minus 50t. So that's a little bit tricky. But Pythagorean theorem, hypotenuse is sum of the square of the legs. The overall distance is the square root of 20t, d1, plus 2 minus 50t, that length there, all square rooted. So there's your function. Do a little bit of simplifying. Multiply these terms out. Take that. And now the first derivative is this long thing here. So pause, set up your critical values, or find your critical values, maybe turn this back into a rational function, find your critical values, and then decide whether the first derivative test with a number line or taking the second derivative is going to be a more efficient way of finding the extrema. So the remainder of the solution is over here. Here's the first derivative. I turned it back into a rational function. Critical values are when the top equals 0 or when the bottom equals 0. The top is pretty straightforward to solve. T equals 1/29th of an hour. The bottom is quadratic, so I started with the discriminant and found out that b squared minus 4ac was negative, which means this has no real roots, so the denominator will never equal 0. So the only critical value is 1/29th of an hour. Taking test numbers of 0 and 1 and plugging them into the derivative produces a negative first derivative and a positive first derivative, which means the distance is decreasing than increasing. So by the first derivative test, there is a minimum distance when t equals 1/29th of an hour. To find out that actual minimum distance, take 1/29th and plug it into the original function. Over here, doing a little bit of work that I didn't show, you wind up with this distance as your answer. So going back and making sure that you've answered the questions, find the time at which they are closest, 1/29th of an hour. Approximate the minimum distance. Plugging 1/29th into that distance function produces this here. So they would probably tell you to round it to 2 decimal places, but this is the exact answer. Okay, so optimization, the hard part is usually taking the written information and turning it into a function. And then when you have a function, the pattern is just going to be first derivative, critical values, and then decide whether to do the first derivative test or the second derivative test. These problems tend to be a little bit challenging, so be sure to work with your friends and try and figure out how to do the homework.